In this video we're going to be revising crystal structure. So our aims for this video are basically based on the 4 different types of crystal structure that you learn about: ionic, metallic, giant covalent and molecular. You need to know how to spot whether a substance has one of these crystal structures. We'll have one of them, but which one it is, and what properties it has because of the fact it has that crystal structure. Now the exam board are very clear on the different, on the substances that you need to know the crystal structure for, and also to be able to draw the structure of. So that's sodium chloride, magnesium, diamond, graphite, iodine and ice. Now from knowing these 6 different substances, the exam board may also ask you to draw other substances based on the fact you know these. They'll say that this is like sodium chloride, therefore you can draw it. So we're going to start with ionic crystal structure, and the first thing we need to do is to know how to spot whether a substance has an ionic crystal structure, whether it's ionic or not. Basically, ionic compounds are substances that are made up of non-metals and metals. So if you have something from this side of the periodic table, the right-hand side, bonding with something from the left-hand side of the periodic table, then you'll get an ionic substance, and you can use that as a rule. So which one of our 6 is an ionic compound? Well, magnesium is just by itself, diamond is made of carbon, graphite is made of carbon, iodine is just iodine, and ice is water, which is H2O, which is hydrogen and oxygen, none of which are metals. Sodium chloride, however, sodium is a metal and chlorine is a non-metal, so sodium chloride has an ionic crystal structure. And the first thing you need to be able to do is draw the sodium chloride crystal, and you must make sure you do it in 3D. And basically, as long as you draw a cube, you'll get all the marks. So if you drew this, you get all the marks. You'll see that there are alternating positive and negative ions in a cubic lattice, if you like. And that will get you full marks in an exam for drawing it. If you want to describe what ionic bond is, you'd say it was the strong electrostatic attraction between oppositely charged ions. And because of this strong electrostatic attraction, it has certain properties. It has a very, very high melting and boiling point. All ionic compounds do, because these bonds are very strong. And also, to boil it, you have to break all of those bonds. Also, because these ions are locked in place, they cannot move. Now, the conduction of electricity requires the movement of a charged particle. Now, these are charged particles, but they cannot move, and so this cannot conduct electricity in its solid form. However, if these bonds were broken, and then these ions were allowed to move, such as in a liquid, then ionic compounds can conduct electricity. So they can conduct electricity in a liquid, but not in a solid. So they have a high melting point due to the fact they have lots and lots of strong ionic bonds that must be broken, and cannot conduct as solid, but can as liquid. So if you melt an ionic compound, the bonds will break, and that will release the ions to be able to move. So the next crystal structure down on our list was the metallic crystal structure, and these are very easy to spot. Basically, if you have a metal, it's going to be bonded together with metallic bonds. So any of these are going to be metallic. They will be held together by metallic bonds and therefore have a metallic crystal structure. So any metal by itself, elemental metals, will be metallic crystal structures. So which one from our list? Well, magnesium. magnesium is our metal, and so that's the one that has a metallic crystal structure. So again, the first thing you may be asked to do is to draw a diagram of magnesium, for example. And what you do is draw ions, and these are positively charged, and make sure you do at least 2 rows, and I would do 3 just to make sure. And they must have an irregular arrangement, so you'll see that each ion is on top of another one. They can't just be all mixed up in random arrangements. And these are all positively charged, these are metal ions. And in a metallic crystal, using metallic bonds, these metal ions are held together by electrons that flow in between them. So what you can do is just draw E's in between them to represent the electrons. Now at GCSE you will have learnt a definition for metallic bonding, and you have to add a couple of extra words to the definition you learnt at GCSE, so you have to relearn it. So metallic bonding can be described as a lattice, and that's one new word, a lattice of positive metal ions held together by a sea of delocalized, and that's the second new word that you may not have used GCSE, by a sea of delocalized electrons, and that will get you all the mark for a definition. Now compounds that have a metallic crystal structure have a number of different properties. Firstly, they can conduct electricity because these electrons can move throughout the structure. And because the electrons can move and flow freely, they can carry charge as well, so electricity can flow through metals. Secondly, they have a very high melting point because metallic bonds are extremely strong. Metals are also malleable, which means they can bend, they're flexible, they're not brittle, they can bend without breaking, and also ductile, which means they can be stretched out into a wire. The reason why metals are like this is because the electrons can move to wherever they're needed. So if you were to bend a metal, and the metal ions are being moved to a different location, the electrons, or the glue if you like, can move to where it's needed. Similarly with drawing out into wire or stretching it, the electrons can just flow into a different position in the structure so as to hold it together if needed. The next crystal structure down our list is giant covalent crystal structures, and they can't really be spotted from the periodic table. You just really have to know the structures that are giant covalent. The two from our list that are giant covalent are diamond and graphite. So the first one we're going to talk about is diamond. Now diamond is made up of carbon, and the carbon is arranged tetrahedrally in all directions, and the structure carries on forever until obviously you reach the edge of the diamond. So I'm going to try and draw it for you. So what you have is one carbon attached to 4 others. Then each of those is attached to another 4. Now I'm not going to draw them all. So that's my attempt at drawing diamond. Obviously this arrangement carries on forever in all directions. So diamond is made up of carbon atoms that are, each one are joined covalently to another 4. Now what this structure gives diamond is a very high melting point, and it's also very hard because firstly to melt it you have to break every single one of these covalent bonds, and covalent bonds are extremely strong. It also does not conduct electricity because it has no free electrons, and that is a phrase that you can use in your exam. to describe why it does not conduct electricity. So it has no free electrons, high melting point, as you have to break many strong covalent bonds that requires a lot of energy. So make sure when you're describing why diamond has a high melting point, you say what the bonds are that you're breaking. So you break many strong covalent bonds, and you need to say that that requires a lot of energy to do that. Now graphite is another example of a giant covalent crystal structure, and again it's made out of carbon. It's just made entirely out of carbon, but the carbon is attached together in a different way. This time in graphite, each carbon is covalently bonded to 3 others in a hexagonal arrangement. I'm not going to draw them all as dots this time. And then each layer is joined together with van der Waals forces, so weakly bonded together with van der Waals forces, like so. Now, because not all the electrons are used in bonding, there's a free electron in between the layers, and this allows graphite to conduct electricity. So graphite does have electrons that can move throughout structure. They have free electrons that can move throughout structure. So graphite has free electrons. It still has a very high melting point and boiling point, because even though these forces between the layers are weak, the covalent bonds that hold all the carbon atoms together in the main are very, very strong. They're covalent again, and so it's the same reason for diamond, high melting point, because you have to break many strong covalent bonds, which requires a lot of energy. The other thing it's used for are lubricants, and that's because these layers can slide over each other. Layers can slide over each other because the van der Waals forces between the layers are very weak, and so the layers are not strongly bound together. So that's why I use graphite in things like pencil lead, because the graphite will come off the pencil lead onto the paper very easily. And it's sometimes used in lubricants as well, because it is slippery due to this property it has in its structure. Finally, we come on to the molecular crystal structure, and molecular crystal structure basically describes any substance that is only held together by intermolecular forces, for example, van der Waals forces, permanent dipole-dipole forces, or hydrogen bonds. And those compounds are just made up of non-metals. So if you have 2 non-metals joined to each other, then you're going to have a molecular crystal structure holding it together. So out of this list, the 2 substances that are held together by a molecular crystal structure are iodine and ice. Iodine is held together by van der Waals forces, and ice is held together with hydrogen bonds. So first let's talk about iodine. So iodine is I2, and is held together just by weak van der Waals forces. So this means that it has a very low melting point and boiling point. If you heat iodine very, very gently, it'll turn into a purple vapour very easily. So what you'd say is that the iodine atoms, even though the iodine atoms are held together with very strong covalent bonds, the molecules are only held together by weak van der Waals forces, and it's the molecules that you are pulling apart when you melt or boil this. You're not pulling apart all the atoms. When iodine is a gas, it still exists as I2. You are just pulling apart the molecules from each other, and so therefore you are only breaking these van der Waals forces, not these covalent bonds. As there's low melting point due to only having to break weak van der Waals forces, make sure you say what the force is that you're breaking when you describe why it has a low melting point. It also does not conduct electricity because it has no free electrons, which is a phrase that we'll be using over and over again when you talk about why things don't conduct electricity. So ice is the other molecular crystal structure that you have to know about, and it is different to iodine because ice has hydrogen bonds holding it together, as compared to iodine that has van der Waals forces. Ice also has van der Waals forces between the molecules, but the strongest one is hydrogen bonds. So ice is made up of water, which is H2O, and this will form hydrogen bonds between two molecules. If you watch the intermolecular forces video, then hydrogen bonds will be discussed in a bit more detail, but basically you have a bond between, well, it's a force, but we call it a hydrogen bond because it's so much stronger than other forces, a hydrogen bond between the hydrogen and the lone pair on another oxygen. This means that ice has a higher melting point than you'd expect, but still a very low melting point compared to other compounds that have different crystal structures. So again, you'd say that ice has a fairly low melting point because it is only held together by intermolecular forces, but it has a higher melting point than, say, iodine, because the intermolecular force that holds it together is much stronger than the one in iodine. It doesn't conduct electricity because, again, it has no free electrons. Another unusual property of ice is that its solid form, or water rather, its solid form, ice, is less dense than its liquid form, water, and so ice will float on top of water. Now again, if you'd like more detail in that, then you can watch the video on intermolecular forces, as it has more detail. If you'd like any more information on crystal structures, then please come and see me, either in revision sessions or any time that I'm free.